Welcome to The Drowsy Astronaut, where tonight we explore one of the most ambitious concepts ever imagined. The idea of surrounding a star with structures that capture all of its energy. Imagine a future where humanity's hunger for power grows so immense that every city, every machine, every spacecraft depends on the light of a star. And instead of building bigger power plants, we are able to build a colossal network around the sun itself, squeezing every drop of energy it emits to power the next stage of our civilization. This is the story of a Dyson Sphere, a megastructure so vast it defies everyday comprehension. Yet it follows from simple logic about how civilizations grow and what they need to thrive. As we continue, you can relax, work quietly, or drift towards sleep while I describe this centuries-long project, because we will move through the engineering slowly, step by step, making the impossible feel tangible and real. And as always, I would love to know where you are listening from, whether you are under clear skies or city lights, in bed, at work, or somewhere peaceful between the two. Drop a comment if you're comfortable sharing. It is always a pleasure to see how many corners of Earth gather here together. So let us begin. We will start with the basic idea, the why and the what of a Dyson Sphere, and then we will watch humanity build one across 1,200 years, from early mining operations to final completion. The concept sounds like science fiction, structures wrapping a star, but the physics is sound, the engineering is possible, and some scientists believe advanced civilizations must eventually attempt this. Picture a future where Earth's energy needs have grown beyond what solar panels or fusion can provide, where industry spans the solar system and billions of people need power on a scale we cannot yet imagine. The answer lies not in finding more fuel, but in capturing the star itself, using the sun as the ultimate power plant, a fusion reactor already burning in the sky. The idea was proposed by physicist Freeman Dyson in 1960, not as a solid shell, but as a swarm, a cloud of independent collectors orbiting the sun, each gathering starlight and converting it to usable energy. Dyson suggested that any civilization needing vast amounts of energy would naturally build such a structure, and we might detect alien Dyson spheres by looking for stars that glow in infrared but not visible light. His paper was brief, just a few pages, but it sparked decades of thought about megastructures and the future of civilization. And today we explore what building one would actually require, step by careful step. Before we start construction, we need to understand the three main types proposed over the years: a Dyson swarm, a Dyson shell, and a Dyson bubble, and how each solves the problem of capturing starlight in different ways. A Dyson swarm is a loose cloud of millions or billions of independent solar collectors, each orbiting the star on its own trajectory, never touching, coordinated by computers to avoid collisions. This is the most practical design because it can be built incrementally, starting with a few collectors and adding more over decades or centuries until the star is surrounded. Each collector might be kilometers across, thin as foil, covered in solar cells, and positioned at various distances from the sun depending on temperature tolerance and energy needs. The swarm would look like a glittering cloud from a distance, and from inside, like scattered mirrors reflecting the star's light in all directions. A Dyson shell is a solid structure completely enclosing the star, imagined as a rigid sphere with the star at its center, all internal surfaces capturing light. This design appears in science fiction often, But physics makes it nearly impossible, because a solid shell has no net gravitational pull from the star inside and would drift until it collided with it. The material strength required would exceed anything we know, requiring substances that may not exist, and the engineering challenges multiply when you consider thermal expansion, meteor impacts, and structural stability. Most scientists consider solid shells impractical or impossible, so we will focus on the swarm design, which achieves the same goal without the impossible engineering. A Dyson bubble is a variant using lightweight panels held in position by radiation pressure from starlight itself, like solar sails that hover without orbiting, balanced between gravity and photon push. This design could work for some collectors, especially in specific configurations, but it requires precise positioning and offers less flexibility than a swarm of orbiting panels. Most theoretical designs combine elements, using orbiting swarms with some stationary elements, and engineers would likely adapt the design as construction progresses, learning what works best. For our story tonight, we will imagine building a Dyson swarm, starting small and growing over centuries until the sun is wrapped in energy collectors. The scale of a Dyson sphere is difficult to comprehend, so let us start with comparisons and imagine the distance from Earth to the Sun, about 150 million kilometers or 1 astronomical unit. A Dyson swarm at Earth's orbit would form a sphere with a surface area of 280 quadrillion square kilometers, which is about 550 million times the surface area of Earth, a number almost too large to visualize. Even if we covered just 1% of that sphere with collectors, we would need structures totaling 5 million Earth surface areas. And building this requires resources beyond anything humanity has ever attempted. Where would the material come from? And how would we construct something so vast? And how long would it take? And what would we do with all that energy once captured? These questions will guide us through the next 12 parts, each covering roughly a century of construction, as humanity transforms from a planetary species into builders of stellar megastructures. We will start with early mining operations in the 2100s, stripping Mercury for raw materials, and end in the year 3700 with a completed swarm and a civilization living within the light of their captured star. The journey requires patience because megastructures are built by civilizations, not individuals, and generations will live and die seeing only incremental progress, adding their small part to the grand design. But tonight, we can witness the entire arc, watching centuries pass in hours, and perhaps finding wonder in what patient human effort might achieve. Picture yourself floating in space in the distant future, the year 3700, and looking toward where the sun used to shine as a point of light. Instead, you see a vast, glowing sphere, kilometers of solar panels reflecting and absorbing starlight. And the brightness is overwhelming even from this distance, a captured star wrapped in human engineering. Between the layers of collectors, you can see habitats, rotating cylinders where millions live and work, and ships move constantly, maintaining panels and transporting materials. This is what we are building toward, and the journey begins now, with the first small steps in our own solar system. Humanity in the early 22nd century has mastered fusion power and spread throughout the inner solar system. But energy demands keep growing, and projections show that even fusion will not be enough by the year 2500. Earth hosts 12 billion people, Mars has 20 million, and the asteroid belt contains hundreds of habitats with millions more, and all of them need power for life support, manufacturing, food production, and the technologies of everyday life. Scientists calculate that if growth continues, humanity will need the equivalent of 1% of the sun's output by 2400 and 10% by 2600, far more than any conventional power system can provide. The numbers force a conclusion. If we want to continue growing, we must capture the star itself, and that means building a Dyson swarm. The sun produces 3.8 times 10 to the 26th watts of power every second, more energy in 1 second than humanity has used in all of recorded history combined. Most of that energy radiates uselessly into empty space. Only a tiny fraction, about 1/1000th, reaches Earth and powers our biosphere. If we could capture even 1% of the sun's total output, we would have more energy than current civilization could use, and capturing 10% would enable projects we can barely imagine today. We could terraform planets, build generation ships to other stars, run computer simulations of entire universes, or power industries across the solar system without any resource constraints. This is why advanced civilizations might build Dyson spheres, not from ambition alone, but from necessity. As energy needs grow exponentially and stars offer the only power source sufficient for a truly spacefaring species. Freeman Dyson argued that such structures might be common in the galaxy, that any civilization lasting long enough would eventually need this much energy and would build accordingly. If he was right, then the galaxy might contain thousands of Dyson spheres around distant stars, and we might detect them by their infrared glow, stars that appear dim in visible light but bright in heat. So far, we have found no confirmed examples, but the search continues, and if we build one ourselves, we will become the first Type 2 civilization we know of. The Kardashev scale measures civilizations by their energy use, and we will explore this more in the next part. But tonight, we simply note that a Dyson sphere marks the transition from Type 1 to Type 2. A Type 1 civilization uses all the energy available on its home planet, and a Type 2 harnesses its entire star, while Type 3 would command a galaxy. Humanity in 2025 ranks around 0.7 on this scale, not yet masters of Earth, but growing steadily, and within a few centuries we might reach Type 1 status. Building a Dyson sphere would make us Type 2, a milestone that places us among hypothetical advanced civilizations and changes what we can achieve. So, as we drift toward the technical details, remember the human element, because this is not just about engineering, but about people, families, and communities building something across generations. Workers will mine mercury under the scorching sun. Engineers will design panels that survive solar flares, and children will grow up in orbital habitats watching the star slowly disappear. The project will span 1,200 years from start to finish, and every generation will add their contribution, knowing they will never see completion but building for descendants. This is patience on a civilizational scale, a commitment to a future we can imagine but never personally witness, and perhaps that is the most human thing of all. Let your mind settle now, because the journey ahead is long, and we will move through it slowly, century by century, each step logical and deliberate. We start with material, where it comes from and how we gather it. And then we build, panel by panel, layer by layer, until the sun is wrapped in light. The story continues in the next part, but for now, rest with the concept. A star surrounded by human creation, energy captured and distributed, a future both grand and possible. The question we must answer first is why humanity would undertake such an enormous project. And the answer lies in the relentless mathematics of exponential growth and the physics of energy consumption. Today, in 2025, human civilization consumes about 580 exajoules of energy per year, which sounds enormous, but represents only a tiny fraction of what the sun provides to Earth. If energy consumption grows at just 2% annually, a conservative estimate based on historical trends, then by 2125, we will need 4 times as much energy, and by 2025, 16 times as much. This exponential curve eventually exceeds what any planetary power source can provide, and stars become the only option, not from ambition, but from simple arithmetic. The Kardashev scale, proposed by Soviet astronomer Nikolai Kardashev in 1964, provides a framework for understanding civilizations based on energy consumption across 3 types. A Type 1 civilization commands all the energy available on its home planet, estimated at around 10 to the 16th watts, including solar energy, geothermal heat, and all other natural sources. Humanity today uses about 2 times 10 to the 13th watts, making us approximately a Type 0.7 civilization, impressive by historical standards but still far from planetary mastery. At current growth rates, we might reach Type 1 status by the year 2200, but continued growth beyond that requires tapping energy sources beyond our planet. A Type 2 civilization harnesses the entire energy output of its star, about 10 to the 26th watts for a sun-like star, 10 billion times more than a Type 1 civilization commands. This is not a minor step up, but a fundamental transformation, requiring infrastructure on a stellar scale, structures orbiting the star and capturing its light. A Dyson Sphere represents the defining technology of a Type 2 civilization, the tool that enables such immense energy capture, and building one marks the transition between planetary and stellar civilizations. Beyond that lies Type 3, civilizations commanding entire galaxies. But tonight, we focus on the achievable goal of Type 2, wrapping a single star. Let us imagine what humanity might do with a star's worth of energy, because the scale is so vast that current applications seem almost quaint by comparison. With 1% of the sun's output, we could power 1 trillion people living comfortable lives, or terraform dozens of planets simultaneously, or run computer simulations of breathtaking complexity. With 10%, we could build fleets of generation ships and send millions to other stars, or create artificial habitats larger than planets, or conduct scientific experiments requiring energy levels that dwarf anything possible today. With the full output, we could reshape the solar system itself, moving planets, creating artificial stars, or powering technologies we cannot yet imagine. Energy is the fundamental currency of civilization because everything we do requires it. And information processing, manufacturing, transportation, and life support all consume power at rates that grow with population and capability. Consider computation alone, a growing portion of energy budgets as artificial intelligence and simulation advance. And some futurists predict that future civilizations might dedicate vast energy reserves to running digital worlds and conscious simulations. A single Dyson Sphere could power computational substrates running quadrillions of minds, Entire civilizations existing in software, experiencing rich simulated lives while the physical structure captures starlight outside. This might sound like science fiction, but the physics allows it, and energy is the only real constraint. Manufacturing at stellar scales also requires stellar energy. And imagine industries that produce ships weighing millions of tons, habitats kilometers across, or even entire moons constructed from raw materials. Current manufacturing is limited by available energy, but with a Dyson Sphere, those limits vanish, and production becomes constrained only by raw materials and time. We could build thousands of generation ships simultaneously, each carrying millions to distant stars, or construct ring worlds, orbital habitats so large they have day-night cycles, weather systems, and landscapes. These megastructures require energy on scales that only stars can provide. And that is why advanced civilizations would pursue Dyson construction. Terraforming planets becomes trivial with sufficient energy, because warming atmospheres, processing soil, and transporting water all depend on available power. Mars, Venus, and dozens of moons could be transformed into Earth-like worlds. And the process that currently seems to require centuries might be completed in decades with sufficient energy. You could imagine standing on a newly terraformed world, breathing freely under an artificial sky, and knowing that the energy to create this came from solar collectors orbiting the sun millions of kilometers away. This is the promise of Type 2 status, the ability to reshape worlds according to need and design rather than accepting nature's defaults. Scientific research also benefits because many experiments require enormous amounts of energy, and particle accelerators, fusion research, and exotic physics all demand power that grows with ambition. With Dyson-level energy, we could build accelerators wrapped around the sun, colliding particles at energies that recreate conditions from the universe's first moments. We might unlock new physics, discover particles and forces unknown to current science, or prove theories about the fundamental nature of reality that remain speculation today. Knowledge itself becomes limited only by cleverness and patience, not by the energy budgets that constrain current research. Communication across interstellar distances requires immense power to send signals that remain detectable light-years away. And a Dyson Sphere could power transmitters visible across the galaxy. We could send messages to other stars, beaming information at rates that dwarf anything possible with planetary power sources, perhaps contacting civilizations who are also listening. If they have built their own Dyson Spheres, they might beam back, and the galaxy could be full of Type 2 civilizations communicating at energy scales that make their signals obvious. This is one reason scientists search for Dyson Spheres, because finding one might also mean finding intelligent life. But perhaps the most profound reason to build a Dyson Sphere is simply survival. Because civilizations that do not grow stagnate, and stagnation often leads to collapse. History shows that societies need frontiers, new challenges and opportunities that inspire effort and innovation, and space offers the ultimate frontier if we are willing to pursue it. A Dyson Sphere represents a goal so vast it could unite humanity for centuries. A project that gives meaning and direction to countless lives, each contributing to something greater than themselves. It is not just about energy, but about becoming the kind of species that builds such things, that thinks in centuries and acts with patience. The alternative is to remain bound by planetary limits, accepting stagnation or decline as resources become scarce and energy demands exceed supply. Some argue for steady-state civilizations that limit growth, but history suggests this is difficult to maintain, and civilizations that stop growing often stop innovating. A Dyson Sphere offers a different path, growth directed outward, channeling human ambition into construction that benefits everyone and harms no one, because the sun's energy radiates uselessly anyway. We simply capture what would otherwise be lost and use it to build a future of abundance rather than scarcity. So the answer to why we would build a Dyson Sphere is this: because growth requires energy, and eventually only stars provide enough to sustain an advancing civilization. The Kardashev of scale shows us where we are and where we might go, and Type 2 status represents not an end, but a beginning, the foundation for projects we cannot yet imagine. In the next part, we turn to practical matters, the materials required and where we would find them, because even the grandest vision must begin with resources. But tonight, rest with the knowledge that energy abundance is possible, and that stars burning all around us offer power sufficient for any dream. Picture a future where energy is never scarce, where every home, every habitat, every ship draws from a vast network powered by the sun itself. Children grow up knowing that power is essentially infinite, and their dreams are limited only by imagination and effort, not by the constraints that burden our current civilization. This is the promise of the Dyson Sphere, and the journey toward it begins with understanding what we need and how we might acquire it. We continue in the next part, but for now, let the scale of this vision settle and rest in the knowledge that stars offer more than light. The engineering challenge of building a Dyson Sphere begins with a simple question: and how much material would we actually need to surround a star with energy collectors? The answer depends on the design. But even a partial swarm capturing 10% of the sun's output would require material measured not in tons, but in planetary masses. Let us work through the mathematics slowly, making the incomprehensible scale tangible, because understanding the numbers helps us appreciate both the challenge and the solution. If we built collectors at Earth's orbital distance 1 astronomical unit from the Sun, the sphere at that radius has a surface area of about 2.8 times 10 to the 17th square kilometers. To cover just 1% of that area, we would need roughly 2.8 times 10 to the 15th square kilometers of collectors, which is about 5 million times the surface area of Earth. Now imagine each collector is thin, perhaps 1 millimeter thick on average, counting structure, solar cells and support systems, and made of materials averaging about 2,500 kilograms per cubic meter, similar to aluminum or silicon. The total mass required would be approximately 7 times 10 to the 21st kilograms. Which sounds abstract until you compare it to familiar objects in the solar system. Mercury, the smallest planet, has a mass of about 3.3 times 10 to the 23rd kilograms. So covering 1% of a Dyson Sphere would require about 2% of Mercury's mass. For a complete sphere, capturing all the sun's light, we would need about 50 times Mercury's mass, or roughly half the mass of the entire asteroid belt, or perhaps Mercury plus a good portion of Venus. This is an almost incomprehensible amount of material, but it exists in our solar system, locked in planets and asteroids that we could potentially dismantle and repurpose. The key insight is that we do not need exotic matter or impossible materials, just ordinary metals, silicon and carbon, the same elements that make up existing solar panels and structures. We need them in vast quantities, but they are available if we are willing to mine worlds and asteroids over centuries. Where would we source this material, and which worlds would we sacrifice for the project? Because dismantling a planet raises both practical and ethical questions. Mercury is the obvious first target, because it orbits close to the Sun, making transport of materials relatively easy with electromagnetic launchers or mass drivers. It has no atmosphere, no life, and no significant human settlement in most scenarios. And its composition is rich in metals like iron and nickel, perfect for structural elements. Mercury's mass would provide enough material for a substantial partial Dyson swarm, and engineers have long proposed mining it specifically for this purpose. The asteroid belt offers another resource. Millions of rocky and metallic bodies totaling about 4% of Earth's mass, and already distributed in solar orbit, requiring less energy to access than planetary material. Asteroids contain iron, nickel, platinum, silicon, and other useful elements, and mining them avoids the moral complexity of destroying a planet, though the total mass is less than Mercury. Venus might eventually be considered, a planet with no life and hostile conditions, but dismantling it would be a far more difficult project than Mercury, requiring centuries of additional effort. Most designs assume using Mercury first, then asteroids, and only considering Venus if the project expands to capture nearly all the Sun's output. The process of mining a planet sounds impossible, but it becomes feasible with self-replicating machines and automated systems that build copies of themselves using local materials, expanding exponentially. These are called von Neumann probes after mathematician John von Neumann, who studied self-replicating systems. And the concept is straightforward: a machine that mines, refines, manufactures, and assembles new machines. You send one probe to Mercury, and it builds 2 copies of itself. Then those 2 build 4, and so on, doubling each generation until millions of machines cover the planet. The growth is exponential, and within decades, rather than centuries, Mercury could be swarming with mining equipment, all working autonomously under guidance from orbiting control stations. Each mining machine would extract ore from Mercury's surface, perhaps using solar-powered furnaces to melt rock, and separate metals from silicon and other elements through processes already well understood today. The refined material would be formed into components: structural beams, solar cells, control systems, and then launched into orbit using electromagnetic mass drivers, railguns that accelerate payloads without rocket fuel. Mass drivers can function continuously, powered by solar energy, launching materials into space at rates of thousands of tons per hour from multiple sites across the planet. The material enters solar orbit and is collected by construction facilities, where it is assembled into the panels and structures that will eventually form the Dyson swarm. Manufacturing in space offers advantages over planetary production because microgravity allows construction of structures that would collapse under their own weight on a planet. Panels can be built incredibly thin and light, using advanced materials like carbon nanotubes or graphene for strength without mass, maximizing surface area per kilogram. Each collector might be kilometers across, but weigh less than a large ship, a gossamer structure of solar cells stretched across a frame, oriented to capture starlight and convert it to electricity. The panels would be positioned at various distances from the sun, with inner panels smaller and more heat-resistant, and outer panels larger but receiving less intense radiation. Station keeping becomes critical because millions of panels orbiting the sun must avoid collisions, and each one requires occasional adjustments to maintain its position and orientation. Small thrusters powered by captured solar energy would make micro-corrections. Using ion drives or solar sails that require no fuel, just electricity to expel charged particles for thrust. The panels would be coordinated by a distributed computer network, each one communicating with its neighbors and adjusting its orbit to maintain safe spacing. This swarm intelligence allows the structure to adapt, responding to solar flares, avoiding debris, and reconfiguring itself as new panels are added. Strength requirements for the materials are manageable because panels do not bear structural loads like buildings do. They simply orbit, and the sun's gravity holds them without needing support structures. The only stresses come from thermal expansion, solar radiation pressure, and occasional impacts from micrometeorites, all of which can be handled with proper engineering. Materials must survive temperatures ranging from thousands of degrees near the sun to merely hundreds further out. But ceramics, advanced alloys, and carbon structures can handle these extremes with appropriate cooling systems. Heat is radiated away from the back surface of each panel, facing away from the sun, allowing the structures to maintain stable temperatures despite the intense radiation. Self-replication is key to making the project feasible within centuries rather than millennia, because building trillions of panels one at a time would take far too long even with advanced automation. Instead, the manufacturing infrastructure itself grows exponentially. Each factory building more factories, each construction platform spawning copies that spread throughout solar orbit. The growth rate might double every 10 years initially, then slow as resources become harder to access. But even modest exponential growth accomplishes in decades what linear construction would require for millennia. By the year 2200, we might have millions of automated facilities orbiting the sun. And by 2300, billions, each churning out panels and adding to the growing swarm. The vision might seem overwhelming, but remember that it builds incrementally, starting with a single mining operation on Mercury and expanding step by step. Each generation would see progress, more collectors added, more energy captured, and more infrastructure built, with every step making the next steps easier and faster. Picture standing on Mercury in the year 2150, watching mass drivers launch streams of refined material into orbit, and knowing that those materials will become the panels that eventually surround the sun. You would not live to see completion, but your work would be part of the foundation, and that is how civilizations build across time. In the next part, we begin the actual construction timeline, starting in the 22nd century with the first mining operations and the earliest test panels orbiting the sun. But tonight, rest with the knowledge that the materials exist, that planets and asteroids hold everything we need, and that exponential growth makes the impossible merely difficult. The Dyson Sphere is not beyond human capability. It simply requires time, patience, and commitment that spans generations. We continue in the next part, but for now, let the numbers settle and imagine Mercury slowly disappearing, stripped for parts, transformed into light. The year 2100 marks the beginning of serious planning for solar energy collection beyond what Earth alone requires, and humanity has spread throughout the inner solar system with millions living on Mars, in orbital habitats and in asteroid mining stations. Fusion power has become standard, but projections show that even fusion fuel will become limiting by 2400, and engineers begin discussing the next step, capturing solar energy directly at its source rather than waiting for it to reach planets. The first proposals for a Dyson swarm emerge from studies conducted on Mars and in Earth orbit, and initial skepticism gives way to cautious optimism as the mathematics proves sound and the materials accessible. By 2110, the Solar Consortium, a coalition of Earth governments, Mars, and belt habitats, formally approves funding for a pilot project to test collector technology in solar orbit. Mercury is chosen as the primary material source after extensive surveys confirm its composition and accessibility, and the planet's proximity to the Sun means materials launched from its surface require less energy to reach construction orbits. Robotic missions land on Mercury in 2115, deploying the first experimental mining equipment powered by solar concentrators, and these early systems test concepts that will later scale to planetary levels. The miners extract surface regolith, process it through solar furnaces heated to thousands of degrees, and separate iron, silicon, and other elements using techniques refined over decades in asteroid mining operations. By 2120, the first successful test launches material into orbit using a small electromagnetic mass driver, and engineers celebrate as tons of refined metal arc into space, proving the concept works. Scaling up takes decades because building infrastructure on Mercury requires solving unique challenges, and temperatures on the day side exceed 400 degrees Celsius, while the night side plunges below -170 degrees. Equipment must function in these extremes, using advanced materials and cooling systems that circulate liquid metals to manage heat flow. The first permanent base is established near Mercury's North Pole in 2130, where shadowed craters provide relief from the sun's direct glare, and solar power remains available from nearby elevated terrain. Workers rotate through 6-month shifts, living in underground facilities carved from rock, and their work gradually transforms Mercury from a dead world into the solar system's largest industrial site. By 2150, Mercury hosts 20,000 workers and hundreds of thousands of automated mining machines, and dozens of mass drivers launch material continuously into solar orbit. The launch sites are positioned around the equator, taking advantage of Mercury's slow rotation to launch materials at optimal times for efficient orbital injection. Each mass driver fires several times per hour, accelerating payloads to escape velocity using electromagnetic force, and the payloads follow ballistic trajectories to collection points where construction facilities orbit the Sun. Standing on Mercury and watching these launches would be surreal, seeing streams of material arc silently into the black sky, a planet literally lifting itself into space piece by piece. The first solar collectors are built in 2155, modest panels only 10 kilometers across, designed to test power generation and transmission systems before scaling to larger sizes. These test panels orbit at about 0.7 astronomical units from the Sun, closer than Earth, but far enough to keep temperatures manageable with passive radiative cooling. They consist of thin film solar cells stretched across lightweight carbon frames, and each panel captures megawatts of power, converting sunlight to electricity with efficiency approaching 50%. The electricity is converted to microwaves and beamed to receiving stations on Earth and Mars, where rectifying antennas convert the energy back to usable power without any fuel consumption. By 2170, 300 test panels orbit the Sun, and they provide 1 gigawatt of power collectively. A tiny fraction of what is needed, but proof that the concept works at practical scales. Engineers refine the design with each new panel, learning how to manage thermal stress, how to coordinate orbits, and how to beam power across millions of kilometers. The panels prove remarkably reliable, with failure rates below expectations, and automated repair drones can reach any panel within days to fix damage from micrometeorites or equipment wear. By 2180, confidence is high enough to authorize the next phase, scaling production to thousands of panels and beginning the real construction of a Dyson swarm. Self-replicating factories are deployed to solar orbit in 2185, each one a complex of manufacturing equipment and assembly robots. And these facilities are designed to use incoming materials from Mercury to build copies of themselves. The first factory takes 5 years to construct its first replica, but that replica takes only 4 years, and the third takes 3 as the process is optimized. By 2200, 8 self-replicating factories orbit the Sun, and by 2210 there are over 100, the exponential growth curve beginning to steepen. Each factory produces not just copies of itself, but also solar collectors. And the number of panels in orbit begins growing at an accelerating rate. Picture working on one of these orbital factories in 2220, a structure kilometers long drifting in solar orbit, where you oversee robotic systems that assemble panels from material streams arriving daily from Mercury. The Sun blazes nearby, far brighter than from Earth, and you work inside shielded compartments with thick windows that filter the intense light to tolerable levels. Your shift lasts 8 hours, and you live in a rotating habitat attached to the factory, where artificial gravity from spin helps your body maintain bone density and muscle despite months in space. The work is repetitive but vital, monitoring assembly lines, ensuring quality control, and coordinating with other factories to avoid orbital conflicts as the swarm grows. By 2250, 10,000 solar collectors orbit the Sun, providing 10 terawatts of power, enough to supply several billion people with energy for all their needs, though still a tiny fraction of the Sun's total output. Earth begins receiving significant portions of its energy from the swarm, and fossil fuels are finally abandoned completely, replaced by clean power beamed from space. Mars uses beamed energy to accelerate its terraforming, running atmospheric processors and ice melting stations continuously, and the red planet's transformation speeds up, adding decades of progress in just years. The economic benefits begin to justify the enormous investment, and political support for expanding the project grows as people see tangible improvements in their lives. Mercury, by 2270, shows visible scars from decades of mining, and entire regions have been stripped down to bedrock, leaving flat plains of bare rock. The planet's mass has decreased measurably, roughly 2% gone, launched into space and transformed into orbiting structures. Some people mourn what is being lost, a natural world dismantled, but others point out that Mercury was lifeless anyway, and its sacrifice enables life to flourish elsewhere. The debate over planetary mining continues throughout this century, with no clear resolution, though the mining proceeds because the energy demand keeps growing. By 2280, the swarm contains 50,000 panels, each one larger than the early test models, and the combined output reaches 50 terawatts, about twice current human energy consumption. The panels are coordinated by distributed artificial intelligence, each one communicating with thousands of neighbors to maintain spacing and avoid collisions. From Earth, the swarm is not yet visible to the naked eye, but telescopes show a faint shimmer near the Sun, reflections from distant panels catching light at certain angles. Astronomers joke that humanity is beginning to build its own techno-signature, the kind of structure that alien civilizations might detect if they are looking. The year 2300 marks 2 centuries of continuous construction, and the Dyson swarm has transitioned from experimental project to established infrastructure. 100,000 panels orbit the Sun, providing 100 terawatts, enough energy to power a solar system civilization of tens of billions with abundant resources. Mercury is half consumed, great wounds carved across its surface, and engineers estimate another century before the planet is completely dismantled. The project has become self-sustaining, with energy from the swarm powering the expansion of mining and manufacturing, and growth accelerates as more resources become available. The 3rd century of Dyson construction sees the project transition from infrastructure building to true swarm formation, as hundreds of thousands of panels begin to visibly surround the Sun when viewed from certain angles. By 2320, 300,000 collectors orbit in coordinated patterns, each one positioned to maximize energy capture while avoiding interference with neighbors. The panels are no longer uniform because engineers have developed specialized designs for different orbital distances, with inner panels smaller and more heat-resistant, made of ceramics that survive intense radiation. Outer panels at Earth's orbit and beyond can be larger and lighter, using thin-film solar cells that stretch for dozens of kilometers across frames of carbon fiber. Each panel is an engineering marvel in its own right, a structure kilometers across but weighing only thousands of tons, held together by material strength rather than by gravity or support structures. The panels slowly rotate to track the Sun and maintain optimal orientation, using reaction wheels and occasional thruster burns for adjustment. Power generated by each panel is converted to microwaves or laser light and beamed to receivers scattered throughout the solar system at relay stations, planets, and habitats. By 2340, Earth receives 80% of its energy from the swarm, and terrestrial power plants are mostly decommissioned, kept only as backup for emergencies. Station keeping requires constant attention because even small orbital perturbations accumulate over time, and panels could drift into collision courses with neighbors if not corrected. Each panel carries an autonomous control system, monitoring its position using starlight and communicating with nearby panels to coordinate adjustments. The distributed network acts like a flock of birds, each individual following simple rules that create complex coordinated behavior across the entire swarm. When a panel fails or needs maintenance, it signals for assistance, and specialized repair drones navigate to its location, carrying replacement parts. By 2360, the swarm contains 1 million panels, and the Sun's appearance from Earth begins to change subtly, with slight dimming during certain times of year. The effect is barely noticeable to most people, but astronomers track it carefully, measuring how much light is being intercepted as the swarm grows. Some worry about the psychological impact of a dimmed sun, though so far the reduction is less than 1%, equivalent to slight haze or high clouds. Engineers assure the public that Earth's climate can be managed with targeted energy delivery, and most people accept the trade-off in exchange for abundant clean power. Mercury is 75% consumed by 2380. And the planet has become unrecognizable, a pock-marked sphere with massive chunks missing, looking more like an asteroid than a world. The remaining material will last perhaps 50 more years at current mining rates, and planners debate whether to strip Mercury completely or preserve a small core as a historical monument. Most vote for complete utilization, arguing that preserving a fragment serves no purpose, and the materials are needed to continue swarm expansion. By 2390, the decision is made to consume Mercury entirely, and the last fragments will be mined by 2420, ending the planet's 4 billion year existence. The energy output of the swarm reaches 500 terawatts by 2400, which is about 30 times total human energy consumption in 2025. And this abundance enables projects previously considered impossible. Mars is fully terraformed by 2410, its atmosphere now breathable, and 50 million people live there under open skies without suits or domes. Venus terraforming begins in 2420, using massive solar shades positioned at the L1 point to cool the planet, and atmospheric processors powered by the swarm gradually convert the carbon dioxide to other compounds. Dozens of asteroids and moons are hollowed out and converted to rotating habitats, each one home to millions of people who never touch a planetary surface. Picture living in one of these orbital habitats in 2440, a cylinder 20 kilometers long rotating to create artificial gravity, where the interior surface is covered with parks, lakes, towns, and farms that curve up and over your head. Through windows in the end caps, you can see the sun, now noticeably dimmer than historical records show, surrounded by a faint halo of reflected light from millions of panels. Your home receives its power wirelessly from the swarm, beamed as microwaves and converted locally, and energy costs essentially nothing, meters removed from homes because there is no scarcity to ration. Children grow up never knowing energy limits, and their dreams are constrained only by imagination, not by the resource shortages that shaped earlier generations. By 2450, 3 million panels orbit the Sun, and the swarm is visible from Earth as a subtle glow around the star, like a corona that appears even during the day when viewed through proper filters. The structure has captured about 3% of the Sun's total output, and engineering teams are confident that growth can continue for centuries, eventually capturing 10, 20, or even 50%. Automation has advanced to the point where human oversight is minimal, with artificial intelligence managing most construction and maintenance, freeing people to focus on design and planning. The self-replicating factories number in the hundreds of thousands, each one producing both panels and copies of itself, the exponential growth curve still climbing steeply. Raw material now comes from the asteroid belt as Mercury nears depletion, and millions of small bodies are targeted for mining, each one stripped and processed efficiently. The belt provides a more distributed resource base, with less environmental concern, since asteroids are already fragmented and lifeless, never unified worlds like Mercury. Mining these bodies is slower than planetary operations because of the dispersed distances, but collectively, they provide enough material to sustain construction for centuries. By 2470, Mercury is gone, reduced to scattered debris, and mining operations have shifted entirely to the belt, where work continues systematically. The Dyson swarm becomes the defining structure of the solar system by 2480, more significant than any planet. The largest artifact humanity has ever created by many orders of magnitude. From outside the solar system, alien astronomers would now detect our star as dimmer in visible light, but brighter in infrared. The characteristic signature of a partial Dyson sphere radiating waste heat. We have become what Kardashev and Dyson predicted, a Type II civilization in progress, not yet commanding the full star, but well on the way. The journey continues, and by 2500 the swarm contains 10 million panels capturing 5% of the sun's output, and the expansion accelerates toward the next milestone. By 2500, humanity's population exceeds 200 billion, spread across Earth, Mars, Venus, hundreds of habitats, and settlements throughout the asteroid belt and Jovian moons. This population is sustainable because energy is abundant, and food is grown in orbital farms, habitats, and on terraformed worlds without the limits that once constrained growth. Quality of life is high, with most people living in comfort, their basic needs met by automated systems powered by the swarm's endless energy output. The Dyson swarm has transformed civilization fundamentally, making scarcity a historical concept rather than a current reality, at least for those within the solar system. Some colonies begin sending generation ships to other stars, powered by energy beamed from the swarm during their acceleration phases, and these ships carry millions toward distant systems, spreading humanity beyond the sun's influence. The swarm enables this expansion by providing the enormous energy required to accelerate vessels to significant fractions of light speed, and dozens of ships depart throughout this century, each one targeting a different nearby star. Humanity is no longer confined to one system, and the Dyson swarm is partly responsible, providing the energy that makes interstellar travel practical rather than theoretical. This is one measure of success, not just capturing energy, but using it to spread and explore, becoming a multi-system species as we were once a multi-continental one. The 6th century of Dyson construction witnesses exponential growth reaching its peak, as self-replicating factories number in the millions and the rate of panel production climbs to thousands per day. By 2520, 20 million panels orbit the Sun, capturing 8% of its total output, and the pace of construction continues to accelerate rather than slow. The key to this acceleration is that energy from the swarm powers its own expansion, with more collectors providing more energy for mining, manufacturing, and launching new collectors in a self-reinforcing cycle. Engineers have optimized every process from material extraction to final assembly, and the time required to build each new panel has dropped to mere hours with fully automated systems. Each panel is manufactured in orbit by factories that never sleep, receiving streams of refined material from asteroid mining operations and transforming it into completed collectors. The factories themselves continue to replicate, and by 2540 there are 5 million manufacturing facilities scattered throughout solar orbit at various distances from the Sun. This distributed production reduces transportation costs because materials can be processed near where panels will be positioned, and coordination between facilities is handled by artificial intelligence that optimizes routing and scheduling. The growth rate doubles approximately every 15 years, meaning the swarm's size increases by a factor of 1,000 each century, a pace that seems impossible but follows naturally from exponential mathematics. By 2560, the swarm contains 100 million panels, and the Sun's appearance from Earth has changed dramatically, now visibly dimmed by about 15% compared to historical baselines. This dimming affects Earth's climate, reducing solar input, but the deficit is compensated by targeted energy delivery from the swarm, beaming power to orbital satellites that warm the atmosphere as needed. Earth's weather is now managed rather than natural, with global temperature and precipitation controlled by energy distribution systems that prevent harmful climate shifts. Some people mourn the loss of natural sunlight, but most accept it as the price of unlimited energy, and Earth remains comfortable with managed climate systems. From space, the swarm is now clearly visible as a glittering cloud surrounding the Sun, with reflections from millions of panels creating a shimmer that extends across millions of kilometers. Spacecraft navigating the inner solar system must plot courses carefully to avoid panels, though the spacing is still large enough that collisions are rare, typically hundreds of kilometers between neighbors. The density increases closer to the Sun, where smaller and more numerous panels cluster, and further out at Earth's orbit and beyond, the panels are larger but more widely spaced. This creates layers of different characteristics, an architecture that emerges naturally from engineering optimization. Station keeping has become a sophisticated science because managing millions of orbiting panels requires precise coordination, and even small errors can cascade into larger problems if not corrected quickly. Each panel adjusts its orbit continuously, using ion thrusters that fire 4 seconds per day, making tiny velocity changes that accumulate to keep the panel on its assigned path. The fuel for these thrusters is argon or xenon extracted from asteroids, though some experimental panels use magnetic sails that interact with the solar wind for propulsion without expending any fuel. By 2580, most new panels use magnetic sails exclusively, reducing logistical complexity and allowing indefinite operation without resupply. Accidents occur occasionally, a panel struck by a large meteoroid or a thruster failure causing orbital drift, and these incidents are handled by specialized repair fleets that patrol the swarm constantly. When a panel fails, nearby panels detect the problem through the communication network and alert repair crews, who dispatch drones carrying replacement parts, or, if necessary, dismantle the damaged panel for recycling. The system is remarkably resilient because the loss of individual panels barely affects total output, and redundancy is built into every aspect of the design, ensuring no single failure cascades. By 2600, the failure rate is less than 1 panel per million per year, and most of those failures are repaired within days, making the swarm highly reliable despite its vast scale. Solar flares pose the greatest natural threat because massive coronal ejections can damage panels and disrupt station-keeping systems. And the Sun remains an active star with unpredictable outbursts. Panels are designed with shielding and redundancy to survive most flares, but extreme events can still cause damage, requiring repairs across thousands of panels simultaneously. Early warning systems monitor the Sun constantly, detecting flares minutes before they strike, and panels in the affected region orient edge-on to minimize exposure, like storm shutters closing. By 2620, AI systems can predict flares with reasonable accuracy hours in advance, allowing even better preparation and reducing damage significantly. By 2640, the swarm contains 500 million panels capturing 25% of the Sun's output. And Earth receives almost no direct sunlight, living instead under artificial illumination managed by orbital systems. The transition has been gradual enough that most people barely notice, because climate control maintains familiar temperatures and day-night cycles continue through scheduled lighting. Some preservationists advocate creating windows in the swarm where sunlight can reach Earth directly, but this would reduce energy capture and complicate orbital mechanics, so the idea is shelved. Earth's sky now appears dimmer, with a scattered glow from reflected panel light, and stars are more visible at night than they were historically because atmospheric scattering is reduced. Picture standing on Earth in 2660 and looking up at midday, where the sky glows with soft light from orbital emitters rather than the harsh sun of ancient times. The illumination is pleasant, warm, but not scorching, and you know that high above, millions of panels are capturing energy that powers your home, your food production, your entire civilization. Children learn about the natural sun in history classes, but to them this managed sky is normal, the only one they have known, and they find the old photographs of bright sunlight alien. This is what adaptation looks like across generations. And what seems like lost to the old becomes normal to the young, who grow up in a world transformed. The asteroid belt is substantially depleted by 2670, with 30% of its original mass mined and launched into solar orbit for panel construction. Engineers begin surveying the outer solar system for additional resources, considering whether to mine Jovian moons or even venture into the Kuiper belt for icy bodies that could provide water and volatiles. Jupiter's moons, especially Ganymede and Callisto, hold enormous amounts of water ice, and that water can be split into hydrogen and oxygen for fuel or used directly in habitats and agriculture. By 2680, mining operations begin on Callisto, the outermost large moon, and materials from there are processed and shipped sunward to support continued expansion. The energy output of the swarm reaches 2,000 terawatts by 2690, which is more than 100 times total human energy consumption back in 2025. This abundance enables projects of breathtaking scale, including terraforming all rocky worlds simultaneously, running continent-sized computer simulations, and powering industrial complexes that produce ships and habitats continuously. Humanity's population approaches 1 trillion by 2700, with most living in space habitats rather than on planets, distributed throughout the solar system in rotating cylinders. The Dyson swarm has made this population possible, and without it, scarcity and competition would have limited growth to a fraction of current levels. By 2700, the swarm contains 2 billion panels capturing 40% of the sun's total output, and the growth rate begins to slow slightly as the best asteroid resources are consumed. The sun from outside the solar system would appear distinctly dimmer in visible light, and its infrared signature would be unmistakable, a clear sign of a Type II civilization at work. We have reached a milestone almost halfway to complete coverage, and the journey continues, though the pace will moderate as resources become scarcer and engineering challenges multiply. The next phase involves filling in the gaps, creating layers of panels at different orbital radii and beginning the transition from swarm to shell. The 8th century of construction marks a transition from random swarm to organized structure, as engineers begin coordinating panels into layers, rings at specific orbital distances that provide more efficient coverage. By 2720, the innermost layer is nearly complete. A ring of panels orbiting at 0.3 astronomical units from the Sun, where temperatures exceed 500 degrees Celsius on the sun-facing side. These inner panels are small and robust, made from advanced ceramics and refractory metals, and they capture the most intense radiation, converting it to energy with specialized photovoltaic systems. The inner layer alone provides enormous power, and its completion demonstrates that humanity can engineer structures even in the harshest environment near a star. By 2740, 3 distinct layers are operational at 0.3, 0.7, and 1.0 astronomical units, with each layer consisting of millions of panels in coordinated orbital rings. The architecture is becoming apparent now, not just a random swarm, but a structured shell. though still with large gaps where sunlight escapes, making the structure porous rather than solid. Between the layers, space is left open for navigation and for the habitats where construction crews and maintenance workers live. And these gaps are essential because a completely solid shell would be unstable and impractical. By 2760, the population living within the Dyson structure exceeds 10 billion. People who spend their entire lives between the layers, working, raising families, and maintaining the vast machine that surrounds the sun. Picture living in a habitat positioned between the inner and middle layers in 2770, a rotating cylinder where you experience artificial gravity and Earth-like conditions. Through the windows you can see panels stretching in every direction, the inner layer closer to the sun glowing with captured heat, and the outer layer beyond reflecting starlight. The sun itself is never visible directly, always hidden behind inner panels. But you feel its presence through the warmth radiating from the structure and the constant flow of energy. Your life is defined by the Dyson, your work maintaining it, your community living within it, and your future tied to its continued expansion and stability. Heat management becomes critical as the swarm captures more energy, because every panel absorbs sunlight and must radiate waste heat to avoid overheating. The backside of each panel, facing away from the sun, is covered with radiators that glow in infrared, shedding excess heat into space. This waste heat is what makes the Dyson Sphere visible from outside, a characteristic infrared signature that alien astronomers could detect across tens of light years. By 2780, the structure radiates hundreds of petawatts of heat, and managing this thermal load requires careful design to prevent panels from warping or failing. The layers are spaced intentionally to allow heat from inner panels to radiate outward without heating outer layers, and computer simulations optimize the distances to balance energy capture with thermal stability. Panels in the middle layer orbit at slower speeds than inner panels, and faster than outer ones, following Kepler's laws, which means the structure is constantly in motion. From a distance, the Dyson Sphere would appear to shimmer, with individual panels moving in complex patterns like schools of fish, though the overall structure remains stable. This dynamic architecture is beautiful in a mathematical sense, and some artists create works inspired by the orbital mechanics, visualizing the dance of millions of panels. By 2800, 50% of the sun's output is captured, and the swarm has transitioned to what engineers call a shell, though it remains porous with intentional gaps. Earth by now is entirely dependent on the structure for energy, and natural sunlight has become a historical memory preserved only in recordings and virtual simulations. Some people live their entire lives without ever seeing the naked sun, and to them, the managed light of the Dyson is simply reality, as normal as air or water. The psychological shift is complete. Humanity has adapted to living inside its own creation, and the structure feels less like construction and more like environment. Venus is fully terraformed by 2820, its atmosphere now Earth-like after 4 centuries of processing, and 100 million people live there under skies that remain cloudy but breathable. Mars hosts 500 million, and the asteroid belt habitats contain 2 billion more, and the outer moons of Jupiter and Saturn are being developed for settlement as well. The Dyson provides energy for all of this, making terraforming and habitat construction trivial compared to the challenges of earlier centuries. And population growth accelerates because resources are no longer limiting. By 2840, the solar system population reaches 2 trillion, and most of those people live in space habitats positioned within or near the Dyson structure. Governance of the Dyson becomes a complex political challenge because the structure spans the entire solar system and affects everyone. Who decides where new panels go? Who manages energy distribution? And who resolves conflicts when panels interfere with navigation or habitat placement? By 2850, the solar assembly is restructured to give representation to Dyson workers and habitat populations, ensuring that those who build and maintain the structure have voice in its governance. Political movements arise advocating for Dyson independence, arguing that the structure and those who live within it should be autonomous from planetary governments, and tensions simmer throughout this century. The view from Earth in 2860 shows a sky filled with scattered light from countless panels, and the horizon glows faintly at all times, day and night, from reflected and re-radiated energy. Astronomers on Earth can no longer see distant stars clearly without space-based telescopes, because the Dyson's light pollution overwhelms ground observations. This bothers some, but most accept it as the price of the energy abundance that defines modern life. And astronomical research has shifted entirely to observatories outside the Dyson or in the outer solar system. By 2880, the Dyson structure is simply part of the environment, no more questioned than the existence of Earth itself, an accepted reality for trillions of people. Solar flares and coronal mass ejections continue to pose challenges, and in 2885, a massive solar storm damages thousands of panels simultaneously, requiring the largest coordinated repair effort in history. Fleets of repair drones work for months replacing damaged components, and the event prompts new investment in storm prediction and panel hardening. By 2895, improved shielding reduces vulnerability, and early warning systems give panels hours rather than minutes to prepare for incoming radiation. The Dyson proves resilient, recovering from the damage quickly, and the incident reinforces confidence in the structure's long-term stability. By 2900, the structure captures 60% of the Sun's total output, with 5 billion panels arranged in multiple layers from 0.2 to 1.5 astronomical units. The pace of construction has slowed from its exponential peak because resource extraction has become more difficult as easily accessible asteroids are depleted. Engineers debate whether to mine the outer solar system more aggressively or to accept a plateau at around 70% coverage, and the decision will shape the next centuries of development. For now, the swarm continues growing steadily, adding millions of panels each year, filling gaps and thickening layers, moving toward ever greater completeness. The 9th century focuses less on expansion and more on optimization and refinement, as engineers address the accumulated challenges of managing a structure that has grown to solar system scale. By 2920, orbital mechanics has become a continuous problem, because even with careful planning, perturbations from planets, solar wind, and radiation pressure cause panels to drift from assigned positions. Each panel must make station-keeping adjustments weekly or even daily, and the cumulative fuel requirement would be enormous, except that most panels now use propellantless systems. Magnetic sails interact with the solar wind, and solar sails use photon pressure for thrust, allowing panels to adjust orbits indefinitely without consuming any physical fuel. By 2940, advanced AI systems manage the swarm autonomously, with human oversight limited to strategic decisions and handling rare anomalies. The AI monitors millions of panels simultaneously, predicting collisions days in advance and coordinating adjustments across thousands of panels to resolve conflicts. This distributed intelligence operates faster than human managers ever could, and the swarm functions like a living organism, self-regulating and adapting to changing conditions. Some philosophers argue that the Dyson has become sentient, though most dismiss this as metaphor, viewing the AI as sophisticated but not conscious. Communication across the structure faces light speed delays because even at light speed, signals take minutes to cross the distance from inner to outer panels. This means real-time coordination is impossible, and the AI must operate with local decision-making, each region managing itself while coordinating asynchronously with distant regions. The system works surprisingly well, using predictive algorithms and cached instructions, but occasionally miscoordination occurs, requiring human intervention to resolve conflicts. By 2960, communication protocols are refined to minimize these issues, and the swarm operates smoothly despite the inherent delays. Collisions do occur, and in 2965, two panels collide due to a navigation error, creating a debris field that threatens nearby panels and requires immediate cleanup. Specialized cleanup drones are dispatched to collect the fragments, which are recycled into new panels rather than left as hazardous debris. The incident prompts a review of collision avoidance protocols, and improvements are implemented that reduce collision probability by an order of magnitude. By 2975, the collision rate has dropped to 1 per decade, an acceptable level given the vast number of panels and the continuous adjustments required. Solar storms remain the greatest natural threat, and extreme space weather events can damage thousands of panels despite improved shielding. And in 2980, a particularly violent flare damages over 10,000 panels, the worst incident since the 2885 storm. The repair effort takes 2 years and involves tens of thousands of drones and human crews. But the swarm's total output drops by less than 1%, demonstrating the structure's resilience. Lessons learned from this event lead to even better panel hardening, and by 2990, new panels incorporate advanced radiation shielding that can survive all but the most extreme solar events. Older panels are gradually retrofitted with the improved shielding, a process that will take decades but significantly enhances the structure's long-term durability. Maintenance at this scale requires a permanent workforce numbering in the hundreds of millions, with people living in habitats scattered throughout the swarm, close to the panels they maintain. These workers are the backbone of the Dyson, and their communities develop unique cultures shaped by life within the structure rather than on planets or in traditional habitats. They call themselves swarmers, and they view themselves as distinct from planetary populations, with their own traditions, languages, and social structures. By 3000, swarmers number over 500 million, and they argue for political representation proportional to their population and their importance to the structure. Social challenges emerge as generations live and die within the Dyson without ever visiting planets, and some people feel disconnected from humanity's planetary origins, identifying more with the structure than with Earth or Mars. Movements arise advocating for Dyson independence, arguing that the structure and its inhabitants should be autonomous, self-governing, and free from planetary control. By 3020, the Solar Assembly grants limited autonomy to Dyson regions, allowing swarmers to manage local affairs while maintaining coordination on energy distribution and major structural decisions. This compromise eases tensions but does not fully resolve them, and debates over Dyson governance continue throughout the century. By 3040, 70% of the sun's output is captured, and the rate of new construction has slowed to a crawl as easily accessible resources are exhausted. Mining operations have shifted to the Kuiper Belt, where icy bodies provide water, volatiles, and some metals, though the distances involved make extraction expensive and time-consuming. Engineers debate whether to continue toward complete coverage or to plateau at current levels, and economic analyses suggest that going beyond 80% may not be worth the resource investment. By 3060, a political decision is made to target 85% coverage, leaving 15% of the sun's light to escape, primarily for navigation beacons and as a safety margin. Picture the Dyson Sphere in 3070, a structure so vast it defies comprehension, with 8 billion panels arranged in layers from deep within the sun's corona to beyond Earth's orbit. From outside the solar system, the sun would appear as a faint glowing sphere in infrared, radiating waste heat at temperatures around 300 Kelvin, warm but not hot, a clear techno-signature visible across light years. Inside the structure, trillions of people live and work, and the Dyson has become the defining artifact of human civilization, more significant than any planet or moon. Energy is so abundant that it is essentially free, distributed to anyone who needs it without cost or rationing, enabling a post-scarcity economy throughout the solar system. The structure itself is maintained by AI and automated systems 95% of the time, with humans intervening only for complex repairs, design improvements, or handling rare emergencies. Life within the Dyson has become comfortable, and most people alive have never known scarcity, never experienced energy rationing, never worried about power availability. Communication systems have evolved to handle the scale, with quantum entanglement networks providing instantaneous coordination within local regions, though light speed delays still affect system-wide coordination. These quantum networks allow AI systems to function more effectively, sharing data across millions of panels without waiting minutes for signals to propagate. By 3080, the quantum communication backbone is fully deployed, and the Dyson operates with unprecedented efficiency, coordination improving by orders of magnitude. This infrastructure will be crucial as construction continues toward the final phases, where every panel placement must be coordinated with millions of neighbors. Resource extraction from the Kuiper Belt accelerates in 3090 with thousands of automated mining vessels harvesting icy bodies, and the materials are processed locally before being transported sunward for panel construction. The journey from Kuiper Belt to inner solar system takes months even with efficient trajectories, but the scale of operations means materials arrive continuously, feeding the ongoing construction. By 3100, the construction rate has stabilized at several million new panels per year, which is slower than the exponential peak, but still steady progress toward the final goal. The structure captures 75% of the sun's output, and projections suggest reaching 85% by the year 3300, completing the planned configuration. The 10th century focuses on filling gaps and completing the inner layers, as engineers work to maximize energy capture while maintaining structural stability and navigation corridors. By 3120, the innermost layer at 0.2 astronomical units is fully complete, forming a nearly continuous shell of panels that capture the most intense solar radiation. This inner shell alone provides more energy than humanity used in all of history before Dyson construction began, and its completion represents a major milestone in the project. The layer is not perfectly solid because gaps are left for maintenance access and heat dissipation. But from a distance, it appears as a complete ring encircling the Sun. By 3140, 3 more layers are completed at 0.4, 0.6, and 0.8 astronomical units. Each one thicker and more extensive than the last, because surface area increases with distance from the Sun. These layers contain billions of panels each, and the coordination required to maintain them is handled by AI systems that have evolved to manage complexity far beyond human capability. The layers are staggered, with panels in each layer offset from those in adjacent layers, allowing heat to radiate outward and preventing shadowing effects that would reduce efficiency. From Earth, now embedded within the middle layers, the sky is completely artificial, managed lighting that simulates day-night cycles but bears no resemblance to natural sunlight. Earth's population has declined to 5 billion by 3160, as many people choose to live in space habitats rather than on the increasingly artificial planet, and those who remain are often purists who value living on humanity's birth world. The planet is maintained carefully, with climate controlled to preserve historical ecosystems, and large regions are designated as preserves where technology is restricted and nature is allowed to function with minimal interference. Earth has become a museum world in some ways, a place of pilgrimage and historical significance rather than the thriving center of civilization it once was. By 3180, Mars has surpassed Earth in population and economic output, and the center of human civilization has shifted to space habitats within the Dyson structure. Picture visiting Earth in 3190, landing at a spaceport and traveling to one of the preserved wilderness areas, where forests grow under managed light that mimics ancient sunlight patterns. You walk among trees that have never seen the real sun, maintained by energy from the Dyson, but designed to feel natural, as if the planet still orbited in open space. Rangers explain that these ecosystems are reconstructions based on historical records, because natural Earth ecology collapsed centuries ago when direct sunlight was blocked, and what exists now is carefully managed. It feels both authentic and artificial simultaneously. A reminder of what was lost and what can be preserved with sufficient energy and effort. By 3200, 80% of the Sun's output is captured, with 10 billion panels arranged in 7 complete layers and several partial outer layers. The structure's mass is staggering, equivalent to several planet Mercury's, and the asteroid belt has been reduced to 30% of its original mass, most of it transformed into orbiting collectors. Construction continues, but at a slower pace as resources become scarcer and the remaining gaps are harder to fill. And engineering challenges multiply with each percentage point of additional coverage. The debate over whether to reach 90% or stop at 85% intensifies, with economists arguing that the diminishing returns no longer justify the resource investment. Energy output of the swarm exceeds 10,000 terawatts by 3220, which is more than enough to power the solar system's 5 trillion inhabitants with energy to spare. Excess energy is used for ambitious projects, including powering generation ships to other stars, running massive computer simulations, and conducting scientific experiments at unprecedented scales. Some energy is even beamed to colony systems light years away, helping nascent Dyson construction at other stars where human settlements are attempting to replicate our success. The abundance is so extreme that energy has ceased to be a meaningful constraint on any activity, and civilization is limited only by raw materials, time, and imagination. Interstellar commerce has become viable, due to the Dyson's energy output, with powerful lasers beaming energy to light sails that accelerate cargo vessels toward nearby star systems. These vessels reach 10% of light speed, making journeys to Proxima Centauri feasible in 40 years rather than centuries, enabling actual trade rather than one-way colonization. By 3240, a dozen nearby systems host human colonies, and several have begun their own Dyson construction, though all are centuries behind the solar system's progress. The solar system Dyson serves as both model and energy source for these distant projects, beaming power across light years to help accelerate their development. Scientific research flourishes with unlimited energy, and particle accelerators now wrap around the Sun at various orbital distances, colliding particles at energies that recreate conditions from the universe's first microseconds. These experiments have led to breakthroughs in physics, including confirmation of theories about quantum gravity and the discovery of several new fundamental particles. The knowledge gained transforms technology, enabling better power systems, faster-than-light communication through exotic quantum effects, though actual faster-than-light travel remains impossible according to current understanding. By 3260, humanity commands physics at a level that would seem like magic to earlier generations, and the Dyson provides the energy necessary to conduct experiments that test the limits of reality. By 3280, the outer layers are nearing completion, with panels now extending to 1.8 astronomical units well beyond Mars orbit. These outer panels are enormous, some stretching hundreds of kilometers across, but they are also extremely thin, gossamer structures that capture the weaker sunlight at greater distances. The engineering required to maintain these panels is complex because solar wind and radiation pressure are weaker here, requiring different station-keeping strategies than inner panels use. By 3290, the final gaps in the outer layers are being filled, and completion of the planned 85% coverage is projected for 3310. The Dyson has become self-aware in a limited sense, with AI systems that understand the structure as a whole and can predict problems decades in advance and optimize configurations for maximum efficiency. Some people argue this constitutes consciousness, while others insist it is merely sophisticated computation. But regardless of philosophy, the AI's management has been crucial to the project's success. By 3300, the AI proposes modifications to the original plan, suggesting ways to reach 90% coverage with acceptable resource expenditure by harvesting materials from Neptune's moons. The proposal is debated in the Solar Assembly, and a decision is deferred to the next century, allowing time to study the feasibility and implications. The 11th century sees the completion of the outer layers and the achievement of the original construction goal, as humanity reaches 85% solar energy capture and considers whether to continue further. By 3320, the outermost complete layer orbits at 2 astronomical units, and panels here are designed for maximum efficiency in the weak sunlight, using advanced materials that capture even infrared radiation. The view from these outer panels is spectacular, the Sun now appearing as a brilliant but distant star, and behind you the structure stretches inward, layer upon layer, visible as a glowing spherical shell. Living and working on the outer frontier attracts adventurous types, people who enjoy the sense of building at the edge, adding the final pieces to humanity's greatest construction. By 3340, 85% coverage is achieved, with 12 billion panels capturing most of the Sun's output while allowing 15% to escape for navigation and safety margins. The escaped light is carefully managed, directed through specific gaps that serve as navigational beacons for ships traveling through the solar system. And these beacons are visible from light years away, marking our system for any observers. The completion is celebrated across the solar system, though it is understood as a milestone rather than an ending, because discussions immediately begin about whether to expand to 90% or even higher. Advocates for expansion argue that we have the technology and that capturing more energy enables even grander projects, while opponents point out that resources are scarce and the current level provides more than sufficient energy. Earth hosts a ceremony in 3342, bringing together representatives from all inhabited regions, including distant space habitats and interstellar colonies, and the event is broadcast to every settlement, reaching audiences of trillions. The ceremony includes historical presentations showing Mercury's transformation, the early test panels, the exponential growth phase, and the gradual completion of each layer over 12 centuries. Speakers acknowledge the countless workers who built the structure, the generations who lived and died seeing only incremental progress, their individual contributions, small but collectively transformative. It is a moment of reflection on what patience and collective effort can achieve, and many people feel connection to ancestors who began this project believing their descendants would see it through. By 3360, the decision is made to expand to 90% coverage, driven by proposals for mega projects that would require the additional energy, including moving planets and constructing artificial stars. Neptune's moons are targeted for mining, particularly Triton, whose unusual retrograde orbit suggests it was captured and could be sacrificed without disrupting the natural system. Mining operations begin on Triton in 3365, using techniques refined over centuries of planetary dismantling, and materials begin flowing sunward for construction of additional panels. By 3380, the expansion is well underway, and new layers are being added at the outer edge, pushing the structure's boundary to 2.5 astronomical units. Picture living on a construction habitat orbiting at the expanding edge in 3390, where your job is assembling new panels from materials arriving from Triton and other outer system bodies. The work is satisfying, adding to humanity's greatest achievement. And you know that your grandchildren will see the completion of 90% coverage, the next major milestone. The community on your habitat is tight-knit, families who have worked on the Dyson for generations, and stories are passed down about ancestors who worked on Mercury or the first test panels centuries ago. There is pride in this continuity, a sense of participating in something larger than individual lives. And the Dyson defines your identity more than any planetary origin or cultural background. Energy distribution has become so efficient by 3400 that every inhabited location receives unlimited power, and some regions face problems of excess capacity, more energy than can be used productively. This leads to creative uses, including massive art installations that consume petawatts, sculptures of light and energy visible across the solar system, expressing human creativity at civilizational scales. Some habitats dedicate energy to running simulations of entire historical eras, allowing people to experience life in ancient Rome, medieval Europe, or early space-age Earth through immersive virtual reality. The abundance of energy has made almost everything possible, and society grapples with questions of meaning and purpose when material needs are trivially satisfied. Philosophical movements arise questioning whether the Dyson has been worth the cost, arguing that dismantling planets and transforming the solar system has separated humanity from nature irreversibly. Others counter that nature is whatever we make it, that the Dyson is as natural as a bird's nest, a tool built by conscious beings to meet their needs. These debates play out in forums, publications, and virtual spaces, and while no consensus emerges, most people accept the Dyson as simply the reality they inhabit. By 3420, younger generations view the Dyson as eternal, having no memory of a time before it, and the philosophical debates feel abstract rather than pressing. By 3440, 90% coverage is achieved, with 14 billion panels capturing almost all the sun's energy output. The 10% that escapes is carefully managed, used for navigation, research that requires natural sunlight, and as a safety margin in case large sections need to be shut down for maintenance. The structure now represents the pinnacle of human engineering, a construction that has endured for 13 centuries and shows no signs of degradation despite its age. Materials science has advanced to the point where panels are expected to last millions of years, with periodic maintenance but no need for wholesale replacement. From outside the solar system, our star would appear as a distinct techno-signature, a dim red glow in infrared that is clearly artificial. Nothing natural produces such a spectrum. If alien civilizations exist and are watching, they would certainly notice the transformation of our sun over the past millennium, recognizing it as the work of intelligent beings. Some scientists argue that the Dyson has made us visible across the galaxy, and that we should expect contact or at least observations from other civilizations within centuries or millennia. So far, no contact has occurred, suggesting either that intelligent life is rarer than hoped, or that advanced civilizations typically choose not to communicate for reasons we cannot yet understand. The solar system population reaches 10 trillion by 3460, with most people living in space habitats rather than on planets. Habitats come in countless designs, from traditional rotating cylinders to exotic configurations using magnetic fields for artificial gravity, and some habitats are so large they contain millions of people with their own weather systems and geography. The Dyson powers all of this, making the construction and maintenance of these habitats trivial, and population growth continues because resource constraints have essentially vanished. Birth rates vary by culture, but overall humanity expands steadily, and some projections suggest reaching 100 trillion within a few more centuries. By 3480, several other star systems have completed their own Dyson spheres, human colonies, that followed the solar system's template and now command their stars. Laser communication between these systems enables cultural exchange. And the solar system, Dyson serves as the elder, offering advice and sharing innovations with younger civilizations. A loose confederation emerges, not a political union, but a network of cooperation. And humanity is no longer confined to one system, but spread across dozens, each commanding stellar energy. By 3500, humanity has truly become a Type 2 civilization, or rather, a collection of Type 2 civilizations connected by culture and communication across light years. The 12th century of Dyson construction sees the structure reach maturity and full self-sufficiency, as remaining gaps are filled and the system stabilizes into a configuration that could last geological timescales. By 3520, 95% coverage is achieved after mining Uranus's moons for additional materials, and only 5% of the sun's light now escapes, used exclusively for essential navigation and scientific research. The structure contains 18 billion panels arranged in 12 complete layers, each layer optimized for its distance from the sun, and maintaining itself through AI coordination and automated repair systems. From outside, the solar system would appear as a faint infrared sphere, nearly invisible in optical wavelengths, but glowing steadily in heat, a clear signature of advanced civilization. The Dyson is now essentially self-maintaining, with the AI systems evolved to anticipate problems centuries in advance. And human involvement is mostly supervisory, setting broad policy while the structure manages its own operations. Repair fleets patrol continuously, replacing worn components before they fail. And new panels are built only to replace old ones, no longer for expansion, because the structure is essentially complete. The population living within the Dyson structure itself exceeds 1 trillion by 3540, people whose entire lives revolve around maintaining and living within the greatest artifact humanity has ever built. These Dyson dwellers, or swarmers, have developed distinct cultures, with languages that reflect their unique environment, living between the layers of an artificial shell. By 3560, the structure has been stable for decades without any major incidents, and engineers declare it complete, no further modifications planned unless dramatic new needs arise. The energy output is used for increasingly ambitious projects, including attempts to move planets into more favorable orbits using sustained laser pressure over centuries. Jupiter is being nudged gradually outward to provide more space in the inner system, a project that will take thousands of years but is enabled by the abundant energy available. Some scientists propose using the Dyson's energy to create artificial stars, miniature fusion reactors that could be positioned anywhere in the solar system to provide local light and heat. Scientific research has advanced to the point where fundamental questions about reality are being answered, and experiments powered by the Dyson probe the nature of consciousness, the structure of space-time, and the possibilities of other dimensions. One breakthrough in 3575 demonstrates that information can be transmitted backward in time over microscopic intervals, opening possibilities for technology that seemed impossible just decades before. By 3590, time communication devices allow the AI managing the Dyson to coordinate with its own near future, creating feedback loops that optimize operations beyond what any forward time-only system could achieve. This technology is carefully controlled because the philosophical and practical implications are staggering, but it demonstrates that a Type 2 civilization can begin manipulating reality itself, not just energy and matter. Humanity's population across all systems reaches 50 trillion by 3600, with the solar system hosting 15 trillion and the rest spread across 40 colonized star systems. Most of these other systems have begun building their own Dyson spheres, though all are centuries behind the solar system's progress, and the original structure remains the most complete and advanced. Cultural diversity has exploded, with each system developing unique societies. And some populations have modified themselves so extensively that they barely resemble baseline humans anymore. Some have become aquatic, others adapted to high gravity, and still others exist as digital consciousness uploaded into vast computational substrates powered by their local Dyson. The meaning of humanity has expanded beyond biology to encompass any consciousness that traces lineage to Earth, and this inclusive definition is widely accepted across human space. Philosophical debates rage about identity and continuity, but most people accept that adaptation is natural and that maintaining cultural connection matters more than preserving any specific physical form. By 3620, humanity is recognized as a family of related civilizations rather than a single unified species, and the Dyson spheres around different stars serve as symbols of that family, each unique but all sharing common origins. The Sun itself continues aging, gradually brightening as main sequence stars do, and by 3640, its output has increased measurably over the Dyson's construction period. The structure adapts, with panels adjusted to capture the increased energy and radiate away the additional heat, and engineers predict the Dyson will function for another billion years, before the Sun's evolution requires major restructuring. Eventually, the Sun will become a red giant, swelling to engulf the inner planets. But that lies millions of years ahead, time enough for countless generations to plan and adapt. Some proposals suggest moving the entire Dyson outward as the Sun expands, a project that would dwarf even the original construction, but is theoretically possible with sufficient time. By 3660, the Dyson Sphere is considered humanity's greatest permanent achievement, a structure that has outlived empires, cultural movements, and even entire species that evolved and went extinct since construction began. It is a monument to patience, to collective effort across generations, and to the capacity of consciousness to reshape the cosmos according to need and design. Children born in 3680 are the 150th generation since construction began, and to them the Dyson is simply environment, as natural as air or gravity, never questioned because it has always existed. The structure has become eternal in human consciousness, and most people cannot imagine a solar system without it. Other civilizations in the galaxy, if they exist, might now be noticing our Dyson Sphere, as its infrared glow has been propagating outward at light speed for over a millennium. Within 1,000 light years, any civilization with telescopes could detect the structure, and some scientists speculate that we might receive contact from curious observers within the next few centuries. So far, silence persists, but hope remains that we are not alone, and that other Type 2 civilizations exist out there, perhaps also surrounded by shells that capture their stars. By 3700, the search for other Dyson spheres has identified several candidate stars, dim in visible light but bright in infrared, and missions are planned to investigate these systems over the coming centuries. We have reached the end of our journey through 13 centuries of construction, and the Dyson Sphere stands complete, a shell of panels and habitats wrapping the Sun and powering a civilization of trillions. Living within this structure has become the normal experience for most humans, and only historians and philosophers remember what it was like when the Sun shone directly on Earth without interruption. Picture daily life within the Dyson in the year 3700, where you might live in a rotating habitat positioned between two layers of solar collectors. Your home receives unlimited energy beamed wirelessly from nearby panels, and your children grow up knowing that power, like air and water, is simply available without cost or concern. The view from your habitat shows panels in every direction, some close enough to make out individual structures, others distant and blurred by the haze of reflected light that fills the space between layers. The Sun itself is never visible, always hidden behind inner panels, but you feel its presence through the warmth that radiates from the structure and the constant flow of energy. Ships move constantly through the layers, transport vessels carrying goods and people between habitats, and maintenance drones patrol in swarms, tiny lights that blink and move like fireflies against the backdrop of panels. This is home, the only one you have known, and Earth, Mars, and the planets are distant places you might visit but never truly understand the way earlier generations did. Work within the Dyson varies depending on where you live and what you choose to contribute, because in a post-scarcity civilization, work is about purpose and meaning rather than survival. Some people maintain the structure, engineering, and repair work that keeps the panels functioning, while others pursue art, research, exploration, or community service. Many spend their time in virtual worlds powered by the Dyson's energy, living rich, simulated lives that feel as real as physical existence, exploring possibilities that reality cannot offer. The abundance of energy has made almost any activity possible, and society grapples with questions of meaning when material needs no longer constrain choice. Education in 3700 emphasizes history and philosophy as much as technical skills, because understanding where we came from helps give meaning to where we are now. Children learn about Earth before the Dyson, when sunlight was natural and energy was scarce, and they study the long construction project, the sacrifices made and the patience required to build across generations. Some young people make pilgrimages to Earth to see the preserved wilderness areas, walking under managed light and trying to imagine what natural sunlight felt like. Others visit the museum on Mercury's remnant, a small preserved fragment of the planet left unmined, where exhibits show what the world looked like before it was sacrificed for the greater structure. The Dyson has fundamentally changed humanity's relationship with time, because structures built to last millions of years shift perspective from individual lifetimes to civilizational timescales. People think in terms of what their descendants 1,000 generations hence might need, and decisions are made with consequences measured in millennia rather than years. This long-term thinking has reduced conflict and short-sighted behavior, because when your structures will outlast nations, petty disputes feel insignificant. Some philosophers argue that the Dyson has made humanity wiser, forcing us to consider our legacy in ways that ephemeral civilizations never must. The sun will eventually evolve, expanding into a red giant in several billion years, and long before that day, the Dyson will need to be restructured or moved outward. Plans already exist, refined continuously by AI systems that model stellar evolution, and future generations will have ample time to prepare for the transformation. Some propose abandoning the sun entirely when that time comes, building generation ships to carry civilization to younger stars, while others advocate moving the structure outward and adapting to the red giant phase. Either path is feasible with the energy and technology available, and the decision lies centuries in the future, time enough for thorough consideration. Other star systems with human colonies have followed our example, and by 3712, complete Dyson spheres exist around different stars, each one powering its own civilization of trillions. These systems communicate through laser transmissions and quantum networks, sharing discoveries, art, and philosophy across light years. Humanity has become a multi-stellar species, and the Dyson spheres serve as both power sources and symbols of what collective effort can achieve. Some scientists speculate that the galaxy might be filled with such structures, built by civilizations that reached our level and made the same logical choice to capture their stars. If other civilizations are out there, we might one day communicate, sharing knowledge about Dyson construction, stellar engineering, and the philosophical challenges of Type 2 existence. Such contact would transform humanity again, proving we are not alone, and offering perspectives from species that evolved under different stars with different histories. Until that day, we continue building, learning, and spreading, confident that the Dyson Sphere proves intelligence can shape the cosmos on the largest scales. Looking back across 13 centuries from 2100 to 3700, we can see the long arc of patient construction, from the first mining operations on Mercury to the completed sphere that now defines our civilization. Countless generations contributed small pieces, most never seeing completion, but all believing that their work mattered, that their descendants would benefit from the foundation laid. This is perhaps the most profound lesson, that civilizations are built across time, with each generation adding to structures that transcend individual lives. The Dyson Sphere stands as proof that humanity can think beyond the immediate, can commit to projects spanning centuries, and can achieve what seems impossible through patience and collective will. So, as we reach the end of this journey together, rest with the knowledge that stars offer more than light, that energy is the foundation of civilization, and that with time and effort, even the most ambitious dreams become reality. The Dyson Sphere is not fantasy, but possibility, a future that might await if we choose patience over haste, cooperation over conflict, and long-term thinking over short-term gain. Picture that future, one last time, a star wrapped in human creation, its energy captured and distributed to trillions who live in abundance, building and dreaming across the millennia. This could be our legacy. This could be the path we take. And the journey begins with the choices we make today. The drowsy astronaut thanks you for joining this long voyage through time and possibility. And I hope you found wonder in the scale and patience required to build something truly lasting. Sleep well tonight and let your dreams carry you forward to that distant future where humanity has harnessed the stars and spread across the cosmos. The journey continues, always continues, and the stars await patient builders willing to work across the ages.